Welcome back, students. In this video, we are going to discuss about the Weibull distributions occurring in your Unit 5 of 18MA 41A. A Weibull distribution is a generalization of an exponential distribution. It is also an example of a continuous distribution. Weibull distribution is very popular in reliability and survival analysis. The probability density function of the Weibull distribution with the parameters alpha and beta, wherein alpha and beta both are positive, is given as f of x alpha beta equals alpha by beta power alpha x to the power of alpha minus 1 e to the power of minus x by beta whole power alpha whenever x is greater than or equal to 0 and is equal to 0 otherwise. We have to note that the Weibull distribution can also be represented as WEB of alpha beta, wherein alpha is a positive shape parameter and beta is a positive scale parameter. When alpha equals to 1, the PDF becomes f of x beta equals 1 by beta e to the power of minus x by beta whenever x is greater than or equal to 0 and is equal to 0 otherwise. So here you can see that this is nothing but the exponential distribution which you have learned in your previous course. So the below graph gives you the comparison between the Weibull distribution and the exponential distribution. So here you can see that when alpha equals to 1, you see an exponential graph. And the next graph gives you the Weibull distribution, wherein we have changed the parameter b. So here alpha is constant with alpha as 10 and beta is ranging from 0.5 to 2. So here we will look at on how to find the mean, variance, as well as the standard deviation and the cumulative density function of the Weibull distribution. The Weibull distribution X with parameters alpha and beta, the expected value or the mean is given or calculated using the formula beta gamma of 1 plus alpha. The variance is calculated using the formula beta squared gamma of 1 plus 2 by alpha minus gamma of 1 plus alpha whole square, and the cumulative density function is given as f of x alpha beta 1 minus e to the power of minus x by beta to the power of alpha, where x will be whenever x is greater than or equal to 0 and is equal to 0 otherwise. One of the reasons it makes the Weibull distribution popular in reliability and survival analysis is because it has a closed form cumulative distribution function. This is very useful in handling data sets that contain right-censored observations, which come across in biostatics and reliability courses. So now we will look at two examples. So the first example is X is defined to be the time from shipment of a defective product until the customer returns the product. And your X is calculated in terms of 1/10 of a week. Suppose X has a Weibull distribution with parameters alpha equal to 2 and beta equals to 1.5. You're asked to find what is the cumulative distribution function of X, the expected value of the return time and the variance of the return time. And also you're expected to calculate or compute the probability when x will be greater than 5. So the cumulative distribution function is given as below, that is equals to 1 minus e to the power of minus x by 1.5 square whenever x is greater than or equal to 0 and is equal to 0 otherwise. The expected value using the formula mentioned earlier, it is found to be 1.3293. And the variance is given as 0.4828, and the probability when x is greater than 5 is found to be 1.4945 times 10 to the power of minus 5, which is almost equal to 0. That means the probability that the customer returns the defected item after uh, might be 5 weeks is almost nil. Next, we will consider the example where X represents the lifetime measured in hours of a spring that is operated continuously, which has a cumulative distribution function. F of X is 1 minus e power minus x by beta to the power of alpha. Whenever where beta is 1000 and alpha equals to 2, you're asked to find the um, survival of a spring more than 30 hours and the survival of a spring which has been operated for 50 hours, it is going to survive an additional of 30 hours. That means we are asked to find the survival of the spring above 80 hours. So for part A, we are found that probability that X will survive after 30 hours is 0.99. So here X, remember that X represents the lifetime. So in 99% of the um, cases, the springs are going to survive for 30 hours. And beyond that, there is only 0.0001 chance that it would not survive beyond 30 hours. And the next part, we want to find the survival of the spring more than 80 hours under the condition that it has survived for 50 hours. So this is the formula and it is found to be 0.9961. That means here, in cases of 99% cases, it would survive 80 hours if it has survived for 50 hours. So thanks for watching this video. For any further details and problems, you can refer the quick learn notes and reference books in the syllabus. Thank you for watching this video.